So if we think of glaciers as starting with snow, if you look in the top right diagram here, snow, which is composed of little crystals of water, of course, frozen water, a lot of it's actually air. Even within the crystalline structure, a lot of that material is air. But as that snow gets compacted over time, it actually breaks down from its very kind of pretty snowflake crystalline structure and eventually becomes just kind of a tiny little ice pellet. And so the amount of air in that material decreases as it gets compacted and as more material accumulates. And so if you can get snow to accumulate in any given location persistently, and it takes typically hundreds, if not thousands of years to really kind of grow a glacier in most instances, if you can get that snow to slowly be transformed into glacial ice, and if it has sufficient mass, that ice will then start to move downslope under the influence of gravity, and voila, you have a glacier. You've got a glacier on your hands. There's oftentimes some confusion about what a glacier is or isn't. You know, sometimes people hike up into the mountains in August and they see a white patch on the hillside and they assume it's a glacier when in fact it's just maybe a persistent snowfield depending on how much snow we're getting in a given year. In Idaho, we preferentially see glaciers forming on north or northeastern slopes. And that's because those sides of the mountain or the topography are going to be protected from the afternoon sun. It's obviously much easier to grow your snowfield into a glacier if it's somewhat protected from the sun. If it's facing south or facing southwest, it's much more difficult to get glaciers, at least in Idaho, to form. Now, obviously, if you have enough snowfall, or if you go further north into Alaska or Canada, you're at such a high latitude and it's cool enough that the sun isn't as big of a factor, and you can indeed get those glaciers forming on different slopes with different aspects. And so in the diagram here at the bottom left, we can see just a diagram of a glacier. And the place at the top of the glacier, up to the top of the mountain, that's the area where we actually add more mass, more snowfall, which turns into ice that sort of feeds the glacier. That's what we call a zone of accumulation. Of course, as the glacier slides down to lower elevations where it's warmer, that's where the glacier is going to lose some of its mass. And this is what's sometimes called the zone of wastage, or sometimes it's called the zone of ablation. It's basically where we're losing mass. It could be evaporation. It could be melting, obviously, into water, evaporation of that water, or it could be sublimation, where we're turning that ice directly into water vapor gas without actually melting it into water. And in any given glacier, it's kind of a checks and balances, right? So you've got added material at the top and loss of material at the bottom. And it really just depends on the given sort of climate from year to year or decade to decade as to what this glacier is going to do. If it's adding more mass at the top than it's losing at the bottom, then it will move further down and it will advance across the landscape. If, on the other hand, it's losing more at the bottom than it's adding at the top, then the glacier will retreat over time. So it's kind of like, I guess, in a way, it's kind of like your checkbook. You know, if you're saving more than you're spending, then your bank account grows. And if you're spending more than you're saving, then your bank account dwindles. And that's not a good thing. And so that's basically, in a nutshell, just a brief overview of kind of how glaciers form and behave. And there's obviously a lot more detail than that, but hopefully that will suffice. So the main thing that glaciers do in any given landscape is they sort of do two things, and they do them actually simultaneously, but just in different locations. So at the top of the glacier, up in the mountains, in the high peaks, that's where the glaciers do most of their erosion. So that's when the glaciers are actively shaping the landscape by grinding down rock, removing bedrock from the underlying topography, and incorporating that broken, eroded material in the ice itself. So thinking of a glacier as just ice is a bit too simplistic. The glacier actually also has embedded rocks, sand, even tiny clay-sized particles encased in the ice. And those particles can come from a couple of different sources. They can come from rocks falling onto the glacier from the adjacent cliffs. It could be as the glacier slides over the rocks beneath it, the ice can actually pluck and remove rocks that are beneath it, and so those become entrained in the ice as it slides down. But the wonderful thing about this process is it creates some very telltale signs and landforms that we see in a glaciated area. So here we have a picture at the top here of Sawtooth Lake, and we can see, looking to the south here, near Mount Regan, this beautiful U-shaped valley. So glaciers are notorious for turning V-shaped valleys, which are formed by streams and rivers, into much broader U-shaped valleys as the glacial ice passes through that area. We can also see, if you look in the sort of the top right corner of that photo near Mount Regan, you can see a very narrow ridge line, a narrow divide between this basin where Sawtooth Lake sits and whatever the adjacent basin is just to the right. So these are these narrow ridge-like features we call arêtes. There's another photo of one here in the bottom left corner. And this is really where the Sawtooth name really kind of comes into its own, is the glaciers and these knife edge ridges, these arêtes, form this sort of serrated skyline that people see from the valley floor that kind of gives the Sawtooths their name and the reason we kind of name them. This bottom right photo is a beautiful picture up in Redfish Canyon of glacial polish and glacial striations. And so you can see these just beautiful lines on the photo here going left to right horizontally as the glacial ice progressed down the valley. That grit encased in the ice actually not only scoured the rocks below, it actually polished it. This is actually the start of a climbing area called super slabs. And the trickiest thing about climbing up this thing is staying off of the kind of lighter colored material, which is exceptionally slippery and polished and difficult to use as hand or footholds, and putting your feet on these darker blotches here where some of that glacial polish has been weathered through, and you get the granite underneath, which is much more gritty. So just beautiful examples. The bottom left photo is looking north from the trail up to Sawtooth Lake. So nice examples in the high country of glacial erosion. As we move down into the valleys where the glaciers end up, this is where the deposition takes place. So as the glacier advances down into the valleys, now we're entering a region where the ice is melting, the ice is sublimating, it's warmer. And so all that grit and sediment, the boulders, any rocks that are entrained in the ice will get deposited on either side of the glacier and at the leading edge of the glacier. And these are what we call moraines. And so moraines are these ridges of deposited glacial material, which we call till. The bottom right photo just shows a nice typical example of glacial till. It's just a hodgepodge mixture of anything the glacier can carry, and glaciers can carry just about anything. They're incredibly large and powerful. You could put a rock the size of my college campus on the back of a glacier, and it would have no problem transporting that down slope. So a real mixture of big and little rocks, typically kind of angular, but they might be a little bit rounded, but the glacial ice itself doesn't round the rocks. The bottom left photo, you can see a ridge of till, of sediment on either side of this lake here. And so if you sort of imagine this now on the landscape around the Sawtooth, I think you can start to see what we had here only a few tens of thousands of years ago. So we're going to focus on the central mountains of Idaho, and I've highlighted a few of the mountain ranges here, but there's two in particular we're really going to spend time on. So just for reference, for those that might be not from this part of Idaho, we've got Boise over here in the lower left corner, the lava fields of Craters of the Moon near the lower right corner, and then this just incredibly mountainous region that forms the central sort of heart, if you will, of the state of Idaho. Of course, we've got many folks in the Stanley area, and Stanley sits at the base of the Sawtooth along the Salmon River, and right at the foot of these big mountains here. So we're going to focus much of our time tonight on the Sawtooth. We've got the White Cloud Mountains here, the Pioneer Mountains here, the Lemhi Range off to the east, but we're also going to focus on this big mountain range here, the Lost River Range, LRR, Lost River Range. And this has the highest peak in in the state with Bora Peak. So these two mountain ranges, along with others, form some of the most dramatic and captivating scenery that we have in all of Idaho. Both of these mountains are formed by uplift on one side of the mountain range caused by a large active, what we call an extensional fault or normal fault. So in the Lost River Range, that big fault lies on the southwest side or the west side of the range. That's the same fault system that produced the 1983 Bora Peak earthquake, which is the largest historical earthquake in Idaho. At the Sawtooth, our big fault lies on the east side of the range. It's called the Sawtooth Fault, and it's the one that was responsible, at least we think, for the March 2020 earthquake that we had just a few years ago. So in a way, we'll circle back to that. So despite the similarities we see with these two kind of lofty mountain ranges, there's some real distinct differences in their glacial histories that I want us to explore here a little bit. So here's a nice summary of these two mountain ranges. And I want to kind of present this in a way. I want to present this a bit as a riddle or a little bit of a mystery. And it's not like a complicated riddle. Some of you might be able to figure it out already, but I'd like to walk you through some of the evidence, show you some nice photos as well. And then let's see if we can come to a reasonable conclusion as to why we see some vast differences in the glacial history of these two mountain ranges. So in the Sawtooth, we've got high peaks that go up to 9,000 or 10,000 feet or so. On the Lost River Range, it's taller. It's a good couple thousand feet taller than any of the peaks in the Sawtooth. So we have mountains that go into the 11 to 12,000 foot range. The Sawtooths are easily, by far, much more extensively glaciated on both the east and the west sides of the mountains. They show evidence for large, very thick glaciers that extended from the high peaks all the way down to the valley floors, down to an elevation of about 6,500 feet. If you spend some time in the Sawtooth in the high country, you know that one of its beautiful characteristics are the alpine lakes. There are just probably hundreds of these high alpine lakes up in the high country of the Sawtooth. And we also have lakes down in the valley as well, behind some of those moraines that we'll look at. If we contrast that with the Lost River Range, like we said, it's way less glaciated. It has glaciers, but they tend to be just on the east side of the range. And those valleys that had glaciers in them, it looks like those glaciers didn't get nearly as far down the valley floors. And so they terminate at a much higher elevation than what we see in the Sawtooth. And then finally, if you look around the Lost River Range, there's a few lakes here and there, but you could count them on, a couple hands, I suppose. I haven't counted how many there are, but I would guess there's, maybe 10, 20, 30 or so. And they're small. They're not nearly as big as the lakes we see in the Sawtooth Range. And so think about this as we look at some photos here. Think about this interesting contrast between these two mountain ranges. On one hand, we've got the higher peaks, but less of an impact of glaciers and smaller and fewer lakes versus a much smaller mountain range that shows signs of being extensively glaciated with lots of lakes. So let's look at some nice images here that might help a little bit. This is the topography of the Sawtooth. So here's Highway 75 coming from Stanley and Ketchum up over Galena Summit. And then Stanley would be, a few more miles to the north here on the highway. And we've got the Sawtooth Range over here on the left side of the image. And what you can see here is just several spectacular glaciated features. At the high peaks, we can see a lot of these bowls, what we call a cirque, a glacial cirque. This is a place where the ice began for the glacier as it moved down slope. It excavates a sort of depression or a bowl in the high peaks as the ice moves down. And of course, these depressions then become ideal locations for water to accumulate. And that's where we get a lot of these high elevation lakes in the Sawtooth. As we work our way down, though, these alpine valleys, we can see these just beautiful ridges of sediment. This is the glacial till. This is the moraines that formed in these places. So here we have Alturas Lake, Yellow Belly Lake, that's Pettit Lake, Hell Roaring Lake up here. These are all lakes that are present because they sit in this low depression surrounded or encased by these moraines. So at one point we had these big glaciers advancing all the way out onto the Stanley Basin floor. And in some instances, as you can see here with the glacier that was at Hell Roaring Creek, its moraine, comes all the way out and actually somewhat dictates the path of the Salmon River. So the Salmon River has had to change its flow path and channel over time as these glaciers advanced and withdrew. Now, when we look at these moraines here, these kind of rubbly, irregular areas at their terminus, at the end of the lobe, that tells us how far the glaciers extended at their maximum. So the glacier would have come down, retreated. It was a kind of constant, just up and down movement of the glacier back up its valley, or back up into the mountains, down into the valley. But this furthest extent here is recorded by the moraines over time. So that's what it looks like, sort of as a specific type of map view. This is what it looks like using Google Earth. So there's Highway 75 in the foreground, north is to your right. And some of those same lakes we just looked at, we can see those here, but then we can beautifully see these glacial moraines. In fact, the trees tend to prefer the glacial moraines because they contain a mixture of sediment sizes and soils that are pretty well drained. So they get their water and there's more nutrients in these soils on these moraines versus the valley floor, which has a lot of clays and some other material in it that make the trees a little bit harder to grow in. So just spectacular view there, looking to the west at the Sawtooth Range. Here's what it looks like from the top, kind of looking down from the crest of the Sawtooth. This is near Thompson Peak, looking down at one of these beautiful cirques, one of these glacial depressions in the high country where the glacier started. This one's occupied by a small, probably unnamed lake. Maybe it has a name, but I'm not sure what it is. And then you can see as the ice would have flowed down the valley here, you can start to see some of these ridges at the top of the photo, kind of in the haze there. Those would represent the moraines as this glacier came down into the valley down here towards Stanley. Another quick view of the Sawtooth. This is Goat Lake, a real favorite hiking destination for a lot of people. Again, kind of showing the steep walls that surround these cirques, some of those knife edge ridges in the distance, so the arêtes there. This one also occupied by a lake. And then this one we can also see, this was just sort of extra fun for me and maybe for you, is this dark stripe cutting through the granite at the head of Goat Lake, which is a dike. So this is a fracture that magma moved through probably during the Eocene about 50 million years ago, that's filled in with some darker igneous rocks. So really nice shot there of Goat Lake. So now that we've looked at the Sawtooth, let's head over to the Lost River Range and make kind of a similar comparison. So here's Highway 93 in the bottom left corner. If you head down to south on that highway, you'll end up in Mackay and Arco, Craters of the Moon. If you head to the north, you'll end up in Chalice, where if you wanted to, you could get onto Highway 75 and head towards Stanley. We can see the ridge lines. Remember, this is the higher mountain range, but as we look at it, we can see it's not nearly as extensively glaciated. It does have nice cirques. If we look at these little rounded depressions at the high peaks, we see that there's quite a few of those. There's a couple lakes in there, but we do not see much in the way of moraines. And I know I kind of cut this off. I probably should have amended this a little bit. I'll show you some photos looking down some of these valleys, but these glaciers didn't go very far, and they definitely didn't cut down into the landscape as extensively as the Sawtooth glaciers. What's more, you can see that here's the ridge line of the Lost River Range, and notice that there are no cirques for the most part or glacial evidence on the west side of the Lost River Range. And so whatever snow was accumulating here was not accumulating thick enough, and the ice wasn't becoming thick enough to form extensive glaciers at all on the west side for the most part. And even coming down these valleys on the northeast and the east sides of the range, the glaciers are just a lot smaller than what we see in other places. Let's look at some actual photos then here. So here's Bora Peak. That's our tallest point in Idaho, 12,000, what is it, 662 feet, something in that range. And on the east side, again, a nice, beautiful glacial cirque. You can see the rocks here are quite a bit different than what we see in the Sawtooth. Rather than these hard granitic rocks, what we have in the Lost River Range are layered, bedded, sedimentary rocks. These rocks are largely from the late part of the Paleozoic era. So they're around 340-ish million years old. And this is mostly limestone with some beds of sandstone in here. So these rocks actually were deposited at the bottom of the ocean, or in some cases like a beach environment. And now they form the loftiest peaks in the state. And a lot of these limestones have fossils in them as well. But you can see this beautiful cirque here with a small lake. This is a great shot here looking down off Bora Peak down to the east. So you can see the U-shaped valley. That's probably that same lake we just looked at, I'm assuming. U-shaped valley, a nice wide glacial valley here. And then it kind of turns out to the left. And if I had a little bit more of this shot here, which I apologize for, the moraines aren't as nearly as obvious in the Lost River Range as they are in the Sawtooth, presumably because the glaciers were much shallower. You can see that we don't have like a good scale here, but that valley, that U-shaped valley, is much broader and not nearly as deep as some of the canyons we get up in the Sawtooth. And so we could make some measurements here and some guesses as to how thick the ice was. And I think we'd come to the conclusion that these Lost River Range glaciers had substantially much less ice in terms of total thickness of the glacier itself. Here's another shot. This is from near Leatherman Peak, showing some of there's a nice cirque over here on the left side, a nice bowl-shaped depression for ice to accumulate, coming down these glaciated valleys here. But we're at the high peaks here. We're at 12,000 feet looking at these. And by the time you get a little ways down these valleys, the glacial evidence starts to really taper quite a bit. Again, a tiny little lake here, but again, pretty dry in the Lost River Range. I think if you even look at the vegetation and the trees, there's some stark differences there as well, but I'm not as well informed on that, so I won't speculate. The other nice thing we can see here is how beautifully folded some of these sedimentary rocks are in the Lost River Range. Just above this lake here, in the foreground, you can see a beautiful downward bending fold. We call that a syncline. So these layered sedimentary rocks, which were once at the bottom of the ocean, have just been beautifully folded by a previous mountain building event, not the mountain building event that pushed these mountains up, but previously during the Cretaceous, about 70, 80, 90 million years ago, there was another mountain building event that caused these rocks to be deformed. One more look. Now we're going to go over to and look down the west side of the Lost River Range. So this is near Mount Breitenbach. We're looking towards the White Knob Mountains there to the west. There's Mackey Reservoir in the middle ground. And you can see that these west side canyons are more V-shaped, more like the type of shape we would expect to see from water erosion versus glacial ice. So even up here above tree line, where the skier is enjoying the snow, late spring snow here, we just didn't have enough persistent snow to form glaciers during the last ice age 20,000 or so years ago. Okay, so that's what the Lost River Range looks like. So I'm going to summarize it all here. So hopefully I've intrigued you a little bit. If nothing else, maybe entertained you with some nice scenic photos. But remember, what's our conundrum here? Our big dilemma is we've got the bigger mountain range here with much higher peaks. So if we assume that the main control on glacial extent and the thickness of the ice on a glacier is primarily elevation, which is a factor in many places. Typically, as you go higher into the mountains, you get more snow, therefore you can get bigger glaciers. But here in central Idaho, that seems to be not the case. We have the taller mountains here in the Lost River Range that are far less extensively glaciated than the much smaller Sawtooth Range over here. So maybe you figured it out, maybe you haven't. So here's a big clue to this dilemma. What we're going to do is we're going to pick 3 locations, 3 towns, Stanley, Mackey, and Lador, and we're going to look at their snowfall amounts. And so comparing these 3 locations, these towns' snowfall amounts, I think will reveal what I think is the dominant control on the extent of glaciation in these locations. So over here in Stanley, at an elevation of about 6,200 feet, that's the elevation of the town more or less, they get on average, in some years they get more and some years they get less, about 76 inches of snow on average in Stanley. If we move over here to Mackey, similar latitude, similar elevation, we see that the snow drops almost in half here, 33 inches per year on average in Mackay, 6,000 feet. If we come over here to Lador, which again, similar latitude, similar elevations, they only get about 18 inches of snow per year. So what we have here is we have a strong rain shadow component as these storms come in primarily from the west or the northwest. The first thing they run into, the biggest formidable mountain range they run into, is the Sawtooths. And the Sawtooths therefore get a lot more snowfall. Much of the moisture from these storm systems falls over the Sawtooths. As it drifts over here, and this isn't very far. This is maybe, maybe 50, 60 miles from one mountain range to the next. As they get over here to the Lost Rivers, they've got a lot less moisture, and so they drop less snow. And by the time they get over the Lemhi Range, another big mountain range with 11, 12,000 foot peaks, into the next valley over here by Lador, they have even less snow or moisture to fall from the sky. So what we have then in central Idaho, and you really can see this just with the Google Earth image, look how green it is on the west side of the Sawtooths. And as you just move across this image, it gets brown really quick. The green is everywhere in the Sawtooths, except where it's white there in the high peaks with the rocks. But there's not a lot of green in these valleys here around the Lost River Range. So we have sort of I guess it's a double, maybe triple whammy snow rain shadow effect, where we have the Sawtooths, the white clouds, which are up to 10, 11,000 feet. Those suck some of the moisture. And by the time these storm systems get to the eastern part of the state and the Continental Divide in Montana, they've dropped a lot of their moisture in the central part of the state. So I hope you found that compelling. I've always found that a cool story and just a neat little explanation for why we see much more extensive glacial features in the Sawtooths, even though they're a smaller mountain range compared to some of these other loftier ranges. So